started for today's class. Just before we start, a reminder, our midterm number 2 is next week, right? So you guys have it on your calendar. So next Monday, midterm number 2, and then it will be your, I think it will be, so it should be written on your syllabus, 25% of your grade. So you should make sure you study for this one. And then our lectures, so topics covered will be mostly from after your midterm number 1. So it will be lecture 9 to 11. So just 3 lectures for midterm number 2. And then, okay, so same time. So 9 o'clock we will start your exam, and then you can write your exam up to 12. But I think most people will finish before 12, so you can arrange your time. And then questions for midterm 2. Just one thing. So we will try to. So last time we had some questions that were more detail oriented. So like we will try to reduce those ones for this time. I think last time the grade was like pretty much evenly distributed. So we will try to do this as well for midterm 2. So we ideally want to have like normal distribution, so it's easier for us for grading, and also but I think if you guys do very well, it's okay too. It will be good for you. So you just study and I'll try to do well. So this means we will not make it too difficult. So not too difficult, but not too easy. We'll try to fix it somewhere in between. Okay, so any questions for midterm 2? Okay, so if you have anything else, you can talk to me afterwards, or you can email me either way is fine. Okay, so for today, we want to talk about environment. So environment has a lot to do with our, it has a lot of influence on our biological systems. So today we'll look at a case where we can try to simulate what happens when your landscape changes over time. So starting from some kind of landscape, it can be a mountain, it can be a valley, or like different kind of things you can set in the, based on your initial condition. But we'll try to see what happens when you have river or water flowing through. And then over time, it should evolve to a point where the landscape will look different compared to the original landscape. So this is just helping us to implement some of the equations into our simulation. So I think some of you maybe, I uploaded 2 more files today. I forgot, I realized those ones are, so I uploaded a few files on Friday, but I realized some of them are not there. So I included new ones, but let's see, not this one. So one of the files you saw, you might see on your E3, should be this one. So it's a old paper, but of course there are new ones coming, but this is mostly talking about, you can look up details if you want, but today we're mostly talking about just a few important things. So if you're interested, you can look at this entire paper. I think it has more discussion regarding some of the equations we'll be using later. So for instance, I will briefly explain this one today. We'll talk about this one, and then this one too. But some details, like for instance, those ones, like how they derive these things, we will not cover those ones. If you're interested, we know where you can find it. You can find it here. So just letting us know where you can find the resources. So those ones, we will not talk about how you derive this one, but you will be setting those numbers on your simulation, in your simulation today. So you will see N and K later, and I will point those ones out when we encounter those ones. Okay, so it's a lot of equations. But something we'll talk about is even though we don't derive everything, but we're trying to understand, like intuitively, if this one makes sense for all the parameters we use. So this is the file, and then we go back to our slide. So they are interested in understanding why this is the case. And because of it, they developed a model to see how the landscape can evolve over time. And then the things they consider are mostly two things. The erosion, which means like water will erode your landscape, like water causes your landscape to change. Or they also include diffusion. So diffusion, you might remember from our heat simulation. So in our heat simulation, we also look at how diffusion can cause heat to energy to propagate across space. So similar idea for mass. When you have a lot of mass on one side and then very little on the other side, then it can cause your mass to diffuse from one place to another. And we'll be looking at those pictures later, so you see how this one works. Okay, so that's the background. And then, so what does it mean when they talk about here? So uniformly spaced valleys. So like it says this process by which uniformly spaced valleys develop is not well understood, which means we don't understand why this is happening. So it's talking about here in this valley, you see they show a remarkably uniform spacing. So if you go to like, for instance, this is that of California. So a lot of places here in the inner land of California, I think maybe not as much in Taiwan, but like maybe Kaohsiung, yes, kind of similar. Yeah, so like those ones, they have this kind of evenly spaced things, and they don't understand why this is happening. Like when water flows through, like why does it form this kind of thing like this one? It's like why not just like wipe everything down or cause like uniformly I don't know, like just yeah. Why is it this pattern and not something else? So this is something we don't understand. And then they try to explain this one using physical models. So for instance, you can have different kind of evolution. So from very top, it's pretty much not very significant, right? You see a little bit of valleys and a little bit of your hills, like higher and lower points. But over time, you see it gradually forms into something you will see later. It's like gradually it gets closer to the final picture where you have a lot of smaller spacing in between. So a lot of smaller spacing will form in between compared to the original figure. So this is caused by this equation we saw earlier. Actually, not here, but yeah. So equation we'll show you later. So this is one thing we consider. So we look at this case where your z over t, so partial d over partial t. So z is your surface elevation, which means your height, like how high is your landscape. This one will change over time, so we are interested in looking at partial d over partial t. And then on the right-hand side, there are a few things. So rho is density, right? So rho is your density. You have the density of the rock and the density of the soil. And then U is your, I think it might be better to say this way. So, okay, so rho is your rock. So you have rock, you have bed rock, like for your foundation. And on top of your rock will change into soil, right? Because rock is solid, but then it becomes over time it can change into soil, convert into soil, like the things you step on eventually. So there are two things. You have your density, rho rock, and rho soil. Two things. And I always explain this one in a bit. And then U is your conversion. So rate at which the conversion happens from rock to soil. Like how fast does it change? And then the second part is your QS. QS we'll talk about this one next time. So just looking at the first part, does it make sense? So if we try to write this out, I will erase. So remember, next week you need to come for your midterm. But if you cannot make it, please let me know. same mass should stay, while the volume will change. The volume of your rock and the volume of your soil will be different, even though they have the same mass. So if you take this one out, then it should be equal to it should be equal to your volume of your soil divided by the volume of your rock. And then I think this becomes it makes more sense now because okay, so which means when you change from rock to soil, for instance your volume becomes bigger. So like your volume becomes bigger, then it should become higher, right? Because I think just a simple way of writing, so okay, area times your height of your soil, and then area times height of your rock, and then the area is similar. If you're looking at this case, maybe the area is similar, but then your height will be different. Your volume changes, so your height will be different, right? So I think this makes sense why we are writing the first part as the ratio of your density. So this one matters because you will change your volume. If your volume changes, your height should also change. Yeah, so at least it makes sense this way. Okay. Questions for this one? Okay, so on your test, I don't think we'll ask you to derive everything, but we should at least understand why this one makes sense. Like, does it make sense or doesn't it make sense? We need to be able to explain. And then, so this should be the first part. And then the second part will be kind of similar to what we saw from your heat equation. So this delta QS. So this one is essentially if you write this one out in more intuitive way, it's basically your partial Q in the x direction over partial x plus your partial Q in the y direction over partial y. Right? So those two things add up will be equal to your delta QS. Yeah. So those are talking about it's similar to when we look at this case because even though there are two different things, but when we talk about diffusion, your heat will diffuse from higher temperature to lower temperature, right? So your energy will flow from higher to lower. Similarly, for your mass, if you look at this one, if you have a lot of mass here and very little here, then it makes sense intuitively that you should have more, should be flowing from the more to the last one, right? So if you have many here, very little here, then it should flow in this direction. And then based on this similar idea, we said we write this one out as delta QS. And then we will develop this one a little bit more. Okay, so for instance, your QS we can write it out in more detail. So this QS here, QS we write it out as QS is equal to two different components. You have your Qn and your QC. Your Qn plus QC. And then talking about the first part, for Qn, N represents your mass movement. So without water. So the difference is the first part we consider no water. So water is not a consideration. And then the second part we consider what happens when you have water. And then what does this do to your QS? So for instance, mass movement, it can be different processes, landslides or rapid sludge, or it can be just from frost heating. So when you have frost, it can cause your landscape to change. And then smooth out landscape landslides represented. Okay. So for instance, if you have landslides, then it can cause your mass to move from one place to another, even though you don't have much water involved in this process. Okay, so this one, I think it might look familiar because it reminds us of your heat equation, right? So it's like or diffusion. So it's some constant and then C. So gradient of C, right? So slope is very flat. So this one, the absolute value of this one is higher, and this one is lower. If you have this one higher, then your mass movement should be faster. Right? I think this makes sense. Steep and then very fast. So, and then this is just a constant, so it makes sense. And then if you want, you can write it out as Qmx and Qmy. So you can write this part all into two different directions. So you can have x direction and you can have y direction. Okay, is it good or too fast? Maybe if you have questions you can ask, so I know where to stop. Otherwise I'll just continue. Yeah. Okay. So I think maybe if I talk to class, at least equations make sense. So okay. So the second type. Don't worry about this one yet. I think mostly looking at the last part. So you have your QC here, and then we write it as channel erosion. So it has something to do with water, like erosion, so it has to do with water, right? So for this one, it says flow of water debris leads to a shear stress. So basically, it has a setting point. So for instance, if you look at this blue equation, this one it says del dot QC. So everything is in terms of vector. So it's equal to K times your and then you have a 0 before it. Okay, so which means it has a threshold. Below this policy threshold, it just vanishes. But after it passes some threshold, then it will have significant impact. So you will have values contributing to this part. So it just means after a threshold, then erosion will happen a lot more. But before that, it's not going to cause you too much impact. And then, so this epsilon, this one is derived it's written more in the paper we showed you earlier. But so even though there are a lot of constants, I think the most important thing is we look at. So we have gradient. So gradient we talk about is important. So gradient is an important factor for our model. And then you have this collecting area. So like how big your area is when the water flows through is also important. So just important things. And then the rest are constants. So just constant numbers. So those ones, we need those ones, but they're not as important conceptually. But conceptually, we care about so area matters, your gradient matters, then your threshold matters, and so on. Okay, so if you write this out, suppose just neglect this conversion for now. So suppose this conversion is not happening too much in the at this point. Then we mostly look at del dot QS. So del dot QS, we remember it has two components, right? It's coming from QM and QC. Right? QM and QC. So QM we know is coming from here. QM is proportional to gradient of T. QM proportional to gradient of T. Right? So that means when we have so let me do it slowly. So QM we said is so I just neglect all the constants. Proportional to gradient of T. Yeah. So and then here we have okay. And then but we care about delta Q as which is equal to delta. So QS is two things. something proportional to linearity. So it makes sense. You should have 2 times. So del square z. You should have this part, right? And then we don't something of course in between here and then something after. But you should see where this one's coming from. This this square is coming from the fact that you are actually plugging this one again into here. So you have this square. So at least we can check to make sure where this one is coming from. Yeah. So you have already one here. You have another here. You plug this one in, so you still have 2. So and then your QC. So QC, the second part. The second part, we have this whole thing, whole equation here, but you identify your area A and delta Z. So gradient of Z. So you can see if you have your so you still have your A, it's still here. Your Z, gradient of Z is still here. So you can see where this one is coming from. But we can don't need to derive this one, but you should be able to see where this is coming from, and you should be able to match one by one. So this scales will help you go through the paper and also for your simulations. And then K, M, and we'll just set those one as numbers in our simulation. So we will not care about A and B. We don't care today. A, B, A1 doesn't matter. But we'll set those numbers and just input those one into your model. Okay. Questions so far? Good. Okay. So. So the first part we briefly mentioned is coming from the diffusion curve. So mass diffusion, mass flow, mostly no water for this part. And then here A is collecting area, so still here. And then the slope has to do with your gradient of D has to do with your slope. So I think this one we can skip a bit. Okay, so what's this thing we are talking about in real life? So in real life, we might have a lake next to a valley or inside a valley, and then water will cause your valley, the shape of your valley or mountain to change over time. So water will bring more mass, and then or you can keep mass away. So this is one example. What happens when we have more complex things? So you can have like ocean on one side, and then at some point, when the water level goes up, you can have water in between your small valley. And then in this case, you can have a pool here. So if you have a pool, then there are different things on the left side, bottom left side. You can have a draining, and then the drainage point. So this tip here, or in mathematics, is like local maximum point. It can be your draining point where water can flow. So you have different definitions for this kind of ecosystem, and then so we write those one out. Draining area, the pools are here. So pools, draining area here, and then draining points. So drainage points. So drainage points are like here. So if you see this one's on the paper I showed you earlier, then you know where what they are talking about. So it's just some terms we use for this kind of environment. so I put down all the equations. You can find the same thing in the paper. We'll skip this one. We'll skip this one today. This one too. Yeah. So just for reference, well, I'll jump into the computational part. So if you have questions, you can ask now. Otherwise, I'll skip to the computational part. All right, so let's see. So you should have this file too. Let me bring it over. So this one, right? Evolution of the landscape. So for this exercise, we will look at the landscape evolution, and then something you will see here is so you can download the two files. One of them should be your notebook, so notebook file, and another one is your supporting file. So it will be different. You should have, I think, one file should be the Python notebook, and another file should be just Python notebook. So you should have both, and I will show you how you can bring this one into your notebook. So if you open your file, you can execute your code, and then there are different things. So when you make your plot, you will see potentially, so you'll see three-dimensional landscape that you can generate. If you change your parameters, you can change how this one will look like in the beginning. And then secondly, if you look at top-down, so from a two-dimensional point of view, if you look top-down, you can get this kind of map where it will show you the height of each position. So you probably saw this one in your middle school geography class, where you have this kind of color. So from lower height to higher point, so lower to higher, it can show you from top-down. Now, so suppose you executed those things, you downloaded your file, you have your py. So if they're a little complex, so I modified this one a little bit. So I initially, you can do it without vector, but I did a vectorized part. When I was a student, I changed it a little bit. So the file name will be a little bit different. I changed it, but it should also execute on your computer. And then your notebook, you should have this IPY notebook, so Python notebook. So if you execute all the things, you can also change your grid points. So like how many small grids you want, you can change this one. Okay, so of course because the code is like a lot, we will now, it's probably impossible for us to ask you the code on your paper, but we can ask you to explain or conceptually understand like why this case is this happening this way. So we it's like possibly we can ask you. So you can get familiar with this one. And then if you look at interpretation, this one option level, this one fine. I will show you the actual code here. So and then this simulation also includes the ones we briefly discussed. So the K, D, and M. We skip the details, but you can change those numbers as you wish. And of course, we can try to compare or look up what's a normal value. Like, so like when we do simulation, we don't want something too different from real life, right? So you can look up some common values for your K, D, and maybe and then it's possible if you can find those ones. If not, it's okay. Just set it as something else. And then the ocean level. So you can change your ET. You can change how fast the landscape will change over time. Okay, already written. I changed this part. It used to be different, but I changed it when I did it myself. So one thing you need to do is, before you can do anything here, okay, so suppose you come here fresh. Okay, refresh, come here new. Okay, so I don't have anything. Oh well, okay, anyhow. But okay, so if you come here, normally you don't have this file yet. It's here because I uploaded it earlier today. But you have to, mostly you have to upload this file. So if you, this is a py file, 10 times. So you have to upload this file, and it will give you a warning saying, okay, every time you need to upload it, otherwise you will go away. So you uploaded this file, and then it should show up here. So you have your supporting file, py file, on the left side. Once you have this one, then you can actually execute because in the very first cell, you have to use this supporting file. So if you don't have this file here, you actually cannot do anything. And if you're interested, you can change this supporting file. I also made changes to this one before. So if you want to make some changes here, you can do so on this file, but not here, not on this notebook. Okay, so if you execute cell, and then number 2, you can add field. So add field means you write a function. It should be given already. You write a function to generate different fields, because in the beginning it's like just a blank landscape, but you want to add different fields to your system. For instance, like if I show you initially from flat, you want to add one mountain here, add another mountain here. How can you do so? You write a function to generate one mountain, two mountains, and then you can set your locations as you wish. So as you change your code, you can move your mountains around to have different landscape in the beginning. So you have this add field function for this one. So those ones are straightforward. It tells you. So I wrote some comments here. So your rows, columns, dx, y, just your size, and then so those ones I think can skip. And then those ones are the things you change. So physical parameter size. I put 3 signs here because it just reminds me I can make changes here, and I can make changes here easily. So the first one, I go closer. So physical parameters, they decay constant, and then D has to do with your diffusion. So if you remember from this is D, I think it should be somewhere here. So it's a proportional part. Your diffusion constant D, you can, the unit is m squared per year. So, well, of course, when you change this, you can change this value. And K, similarly, you can change your value here. So now it's like 10 to the minus 10 times 10 to the minus 6. Or you can change numbers. Of course, you should make sure it's reasonable, not like crazy numbers that doesn't make sense. You should set reasonable numbers. Maybe on your test we can ask you what's a reasonable number for this one, like a range. We might not ask you precisely, but we can have some like intuition. It's like, okay, roughly what makes sense or what doesn't make sense. And then this uplift, for now we don't care about this one. Set as 0, or you can change it. So this is just your simulation step. Like when you do your simulation with ET, you have your time step. And then now you remember M and N, right? M and N. I think it's coming from 4. Okay, here. So we have K. We saw K already. And then N. Normally there are just some different numbers depending on your parameters. But we can just don't worry about this part. Just set it as some number, and then you can change those numbers directly. So so n is close to 1. You can. This is 7 divided by 10. So it's almost 1. So we just set it as 1. And then n you can change it. Mostly this will change your exponent. So your collecting area it has exponent n. So how many powers you have? And then this is similarly for your gradient it has an exponent n, and we're just deciding how much exponent you want to have. Okay, so delta c, this one you also have it here. Delta c right here, and then we just set it as some number 10. You can change this one too. Okay, so let's see. For simulation time, this is okay. Just help you estimate how long you need for your simulation, because you don't want it to be 2 hours, right? It's like too long. You just want something quick for you to gauge what happens. So iteration, let's say this one I think. So this one is interesting because it will try to do some basic data to give you a general idea. So for instance, it will tell you your minimum elevation. What's your lowest point on this graph? Like what's your lowest point? And then secondly, what's your highest point in this graph? And you can double check confirm with your figure. So your ocean each level, ocean volume. So ocean volume, I think a few weeks ago we had a different way of computing ocean volume. But here we also have it for you to check how much water do you have in your lake, right? So you can have a brief idea and then see if this will make sense. So how much percentage of your ocean surface? So yeah, land versus ocean. Okay, so this is basically you set your initial figure, you have something here, and then you can update your figure every time. So every time you update your figure when something happens. And then I think those ones we don't need to check. Just for you to see. Okay, so now comes to a point where, for instance, this is one example where you added a few mountains in the beginning. You remember the anthill? So you added a few things in the beginning, and then you look at it top down to see if it's one. I just kind of makes sense, right? Because if you see kind of like higher points here, higher points here, higher points here, higher points here, high points here, high points here, high points here, high points here. So you can see like they should match. Two graphs should match. Okay, so far, any questions? Good. Okay, so now you execute. I think this one. Another parameter. Okay, so if I remember correctly, most things you don't need to change. The only things that will change your figure the most are actually the ones I showed you earlier. These parameters will determine a lot of your things on your figure. But what's here might not change that much. So if you execute those things, it will tell you how much ocean volume, ocean level, and ocean surface fraction. So it's like around 10% right now. So that's the beginning. See if I can reduce a little bit. So for this example, it actually changes very slowly. But you should have you should figure out how you can make it change fast. So why is it slow right now? Let's take a look. So maybe if you focus on one thing here. Okay. So this one, no, 1, 2, 3. And in the beginning we have one. How many? Like 1 line, 2 line, 3 line, 4 line. So it's like you have a little bit this one is changing but very slowly. And so if you look at your landscape on the left side, it also changes very slowly. So it changes but it changes slowly. And the challenge for you is, through this example, you should figure out how you can make it different. So if I try to erase, maybe this contrast is working. So you should be able to answer some questions like, how can you make it for landscape? How can you make this landscape change faster? Maybe we can ask you on your test, right? Maybe, so you should figure out, like, out of all the parameters you use, like you have your E, you have your K, you have your M, like so many things. What can cause your landscape to change fast? And then maybe you can see. Okay, so maybe spacing. So we can say, how about your spacing? You remember in the beginning of class, we talked about the initial point, the very reason why we started this experiment in the first place was they don't understand why you have uniformly spaced valleys. Like we don't know why. So we have this simulation, and now you should figure out why. Right? So you can try to figure out, maybe you might have answers, you might not have answers, but you should try to figure out that. What causes this spacing, and how can you change this spacing, if possible. But if not possible, it's okay too, but you should figure out. So, and then lastly, if you have any, if you can generate any interesting landscape. So maybe landscape should generate interesting. It's not very clear, but you can see. So try to generate interesting landscape. So maybe before you go, you can show our TA your answer. Might not have the perfect answer, but you should try. Use the time now, since we might ask you on your class, right? So why not just spend some time, run through this code, and then try to answer for yourself those questions. So you have some basic idea about this one. And then maybe you can show your TA later, and then afterwards you can finish today's model. Yeah, so I think that would be the plan for the next, next lecture. I think this lecture, almost 9:50, but when you started doing this part, you can think about those questions and then try to do it on your own. Yeah, okay, so questions for what we want to do today.
So that's the last one.
Oh, last part? Yeah, sorry, it's not very clear. It says try to generate interesting landscape, like something cool, like be creative and think about what you can do, because you have everything you need, right? Like here I just added maybe 4 mountains, but you have all the things you need. You can use the add function, the add function to add different mountains, and you can see interesting phenomena happening. And if you can have this one, it will be pretty cool. But I guess it's optional, but you can try. Those I think the top 2 are more important because they answer some physical, like real life questions, like how does your landscape change depending on your parameters? So I think those are more useful questions to ask. And this one is interesting and fun question to ask. Yeah. So does that answer your question? Okay, perfect. All right. So you can give it a try, and then feel free to ask you if you have any questions. Yeah, so maybe make sure you can also have this file here. 沙漠，就加州很多沙漠，沙漠的地方为什么它好好的这个地，然后水流过去之后，它竟然会变得就是很均匀分布，然后细细的这个间隔，就是这样的间隔，他们觉得很好奇说为什么是这样，为什么不是那样，而是这样，这是很好的问题，为什么这样？所以假设你能够，我会觉得就是这个是一个很 simple 的 model，所以不见得能够完全达到回答所有问题，但是如果能够给我们一些就是想法说，有可能是什么原因造成，就是可能我调到这个参数，调到这个之后就发现，调到这个之后它的 spacing 就有明显改变，那有可能就是受它的这个参数影响，对吧？所以我们可以就是去把它试着找出来，对，那不见得有一个完美答案，但是至少要去找答案。那第三个就是，如果能够产生一个有趣的就是那个地形的那个变化的话，我觉得会很好玩。就是目前其实是一张图画出来，但是我自己以前我是学生的时候，我们其实是把它做成一个影片，就是你直接可以把它拼接起来，它变一个很棒的影片。所以就是可以等于说就是让这个工具不是只是课堂上在学，就是它能够以后你在做模拟的时候，它可能变成一个很有趣然后很漂亮的东西。那如果你能够现在就产生一个你可以考虑一个复杂一点或者有趣的那个地形，然后它怎么受水流的变化，然后随时改变，我觉得这会非常好玩，所以可以去试试看。然后这个比较第三个比较开放的，就是试试看。这个第二个也是寻找答案。第一个我觉得是比较很明确，就是应该有。